So remember, we're trying to find the slope of this secant line, which in some kind of way is supposed to help me find the slope of a tangent line. You'll see. You'll see how it's going to happen. But I'm tasked with finding the slope between these 2 points. Essentially, I have these ordered pairs, x comma f of x, and x plus h comma f of, there should be an extra set of parentheses there, x plus h. Those 2 points. Another set of parentheses. So I want to find just change in y over change in x. So my slope here should be f of x plus h, that's this one here, minus f of x, this y coordinate, all over, in the same order, x plus h minus x. And I try to simplify it. There's not much that can simplify other than the fact that these x's down here at the bottom can cancel out. And when we do, we get f of x plus h minus f of x over h. Does that look familiar to you? Hopefully it does, because it is something from pre-calculus, which is called a difference quotient. It is essentially just the slope of a secant line between 2 points. It represents an average rate of change, right? It's the same kind of slope that we're always calculating. Sometimes you see this instead of in terms of an h down here, you see it in terms of delta x, a change in x. What does this thing represent? What does this h represent? It is the small little increment that I have to go to the right by. It could be to the left. This picture goes to the right by some small number in order to get a second point on the graph in order to calculate the slope of that secant line. All right, but this is a problem, right? This is a secant line. That's not what I wanted. I wanted the slope of a tangent line. So what I want to do in order to make the tangent line happen, I'm going to decrease the size of that h. I'm going to make it smaller and smaller, as close to 0 as possible, and this is a concept that's called a limit, and it is what the first unit is all about. It's a limit. I'm going to try to make this h right here as small as I can possibly get it. So let me show you that on decimals also. Static picture only goes so far. It is the tangent line problem. Here we go. Let's hide this stuff. And I have the same kind of setup that I had before. I've got these 2 points. The dotted line there is the actual tangent line, and the purple one here is the secant line, okay? And I have these 2 points, P and Q. Do you see this orange segment that's down at the bottom in between 1 and 2? That orange segment that's down there at the bottom, that's essentially h. I have started at point Q. I went to the right by 1 unit, that's my h, in order to find a second point on the graph, a secant line. And so what I'm going to do is I'm going to make that h smaller and smaller and smaller and smaller, closer and closer to Q, and as I get close, P gets closer to Q, and H gets smaller and smaller and smaller, I'm going to get closer and closer to that tangent line. And that's the idea. And that's what the first type of calculus, the differential calculus, does. And that's the solution to the tangent line problem. We're going to use a secant line, and we're going to get closer and closer and closer to the tangent line using some slopes. So as h approaches 0, the slope of that secant line approaches the slope of the tangent line. And that's the solution, that's the solution to the tangent line problem. But that's not the only kind of calculus. There's a second kind of calculus, which it really, really does not seem associated with what we're doing here with tangent lines at all. It's called the area problem. If you did anything on the summer assignment, some of those problems were concerned with the area underneath of a curve for some particular reason. And mathematicians wanted to know, like, how could I find the area underneath any given function? Like, we've got area formulas for triangles and trapezoids, geometric shapes like that, but what about this weird shape? How am I supposed to find the area underneath of this curve? Well, the solution to this one also has to do with an approximation. The secant line is supposed to be an approximation of the tangent line, and how I'm going to calculate the area underneath this weird curve is to use a shape that I could easily find the area of. I'm going to break this up into pieces, and specifically I'm going to break this up into little rectangles here, because I could very easily find the area of each one of these rectangles and add them up. Problem is that it's not very accurate, right? I've got some missing parts. I got some that are on the outside, and I'm missing little pieces here. So how can I make it better? How can I make this approximation better to get a closer approximation of the area underneath the curve? And the answer to that is whatever the width of this rectangle is down here, I'm going to make it smaller. I'm going to make it as close to 0 as possible. And again, that is the idea of a limit, which is the unifying idea of all of calculus. It's going to tie together both the differential calculus and the integral calculus, which is the second kind. So the width of this, as I make it smaller and smaller, closer and closer to 0, it's going to give me the actual area underneath the curve. Right? So again, I have a sketch or a demo. And let's hide that in Desmos. Oh, no, I need that, actually. I'm going to come over here. Because I can change the bounds of where the area is being taken from. Actually, I need to get it back over here. I just don't want to confuse it with some negative stuff. And then I can change the number of rectangles. And you can see as I change the number of rectangles and I make them smaller and smaller and smaller, I'm getting closer and closer to the area underneath that curve, right? I'm getting less and less error. Let's go back just because it's fun. Okay. Right, so this is what calculus does. It takes something that's an approximation and makes the error in that approximation smaller and smaller and smaller with an idea of a limit. Now, at first glance, it doesn't seem like these two problems, really, these two problems are related at all. We've got area under a curve and we've got tangent lines. What's the connection between those two things, and why the heck would I even want to know the area underneath the curve? Fantastic question. And what mathematicians, and in particular Newton, discovered is that these two things are inverses of each other. Doesn't seem like it, but we will see in future lessons that finding the slope of a tangent line and finding the area under the curve, they undo each other like inverse operations in mathematics do. So here's one final question for this part of the lesson. Which of these two classic problems, the tangent line or the area problems, could local linearity help to solve and explain? Well, we kind of already answered that. We kind of already answered that on Desmos when we looked at this graph for the tangent line here, and we were able to zoom in on the graph, and the graph, the function itself, was getting closer and closer to the tangent line. So the answer to that question, of course, is that local linearity helps us with the tangent line problem, and it's associated with the slope of a line at a particular point.